Okay, good afternoon. Right, so today we move on to our third topic in your syllabus, that is representing data in computer. Okay, so now we have done topic one, introduction, concept of ICT. Topic number two, introduction to computer. We have done all the subtopics. Last time we discussed about uh, motherboard and expansion source as well as storage devices. Uh, So you don't get much question from topic two, but you definitely get some MCQs from data representation, at least three MCQs. Okay. And this is one of the smallest topic as well. First, I have subdivided into two subtopic, number bases, representing data in the computer. So when it comes to the syllabus, because you must always keep track of your syllabus and whether it's covered or not. Okay. Right. So now we have finished topic two, fully done. Right. Into the topic three, uh, part one, analysis of how numbers are represented in computer. Right. Need instructions and data representation in digital devices. Method for instruction and data representation. Representing of data in two states, 0, 1. Number systems used in computing like binary, octal, hexadecimal. Conversion between number systems. Then representation. Actually, we are going to do only this part today. That is the number theory part. Number theory part. So the next class we are going to look at how the integers are represented using two's complement and so on. How characters are represented. Okay. Anyway, binary arithmetic operations we are going to do today. Okay. We are going to do today. Right. So other parts we are going to do in the next class. Okay. So we are going to do half of it today. The next half or next quarter, we need three classes. Today we will do half, then another quarter, another part. Okay. So then topic three is also, I told you topic three is the smallest. Okay. Uh, right. So today what we are going to do is not representing data in computer, rather uh, the number theory. Okay. The mathematics part. Anyway, you have done it in your O level, but we are going to do a quick revision. Okay. Very quick revision. Because you get some questions from this part as well, though it's sort of mathematics. Because this understanding is important to proper understand how the data is represented in computer. Okay, right. So let's start straight away. Number bases. Now remember, computer represent everything as quantities. Remember, as humans, we can think of, remember, process two type of data: quantitative data, qualitative data. Like quantitative data like your age, your marks, price of an item. Okay. Or you can just count how many biscuits are there. Quantitative data. And also we can think of qualitative data. So you can listen to music, you can read some text. Those are not quantitative, right? Some newspaper articles, novel, or you can see a painting, picture, right? Movie. Those are not quantities, qualitative things. But for computer, of course, computer also can work with numbers, quantities as well as text, image, audio, video, but these are qualitative. So the big difference is for computer, everything is ultimately quantity. For us, these are quantities, these are qualities. We remember these in different way and these in different ways. We process also different ways. But for computer, everything is set of ones and zeros. and everything is processed using Boolean logic gates and or not gates. Okay, so therefore, that is why this topic is important, number systems, because we even represent image as a number or quantity. We even represent someone's voice as a number. So that is why we are interested in this topic. So that is a big picture. Okay. Otherwise, you don't know why we are interested in this. Right. So when it comes to number, now we are looking at it as a mathematical top subject. Okay. So remember the computer is called computer, right? Computing machine. Only thing is it's not a calculator. Calculator is also computing device. Computer is also computing device. But calculator can only process numbers or represent and process numbers. But computer can represent not only numbers, text, image, audio, video, but as numbers and then process. Because anyway, it's represented as numbers, therefore it's so okay to say computer. It's computing, right? You computing your image related things, text related things. Okay. Right. So when it comes to numbers, because ultimately for compute everything is a number. Now in mathematics, you know that there are different branches. So the main branch is arithmetic. So then you have the algebra, geometry. Okay, so these are the three big guys. So then you have calculus, probability, and statistic, and so on. Now, when it comes to arithmetic, so arithmetic is all about quantities, representing quantities, and doing operations with quantities. Right? So, how do you represent quantities using numbers? Using numbers. So therefore, if you are doing IT, if you are working with computer, where computer represent everything as numbers, so you must be really comfortable with numbers. So remember, arithmetic is the area in maths that we are interested in representing, manipulating numbers or manipulating quantities. So first of all, you must know that there are different type of numbers, right? So there are what is known as integers. Integers are something like 0, 1, 2, 3, -1, -2, -3, and so on. Okay. So then we have real numbers. That means we include decimals as well. Like not only now we have -3, -2, -1, 0, 1, 2, we have zero point 0.5, -0.9, -2.005, or you can say 1.5 or 1/3. When you include all fractions and decimals also, then we call it real numbers. These are called integers. Okay. So when you draw a number line, basically you draw the real number line. Cartesian plane is two real number lines. So therefore you can show something like 5.3 as well as 5.1 comma 2.3 or 5.1 comma -2 -0.7. Right. So therefore numbers are used to represent quantities. So numbers can be integers, numbers can be real numbers, and of course there are some other numbers as well, right? Like imaginary numbers, but we are not interested in those. Now, whenever we represent a quantity using number, something like 5 or 12 or -3 or half or 0.75, there's a concept behind this. What is that concept? Whenever we represent a number, of course, the modern number system is called Hindu Arabic numbers. Hindu Arabic numbers. You know that there are two different type of numbers. So this background is super important, which you have learned in your O-level maths. So this is called Hindu Arabic numbers. Hindu Arabic numbers, the modern number system. And before Hindu Arabic number system came, we had different type of number system: Babylonian numbers, Greek numbers, Roman numbers. For example, if you take Roman numbers, it's like very primitive 1, 2, 3, 4. Then you have something like 9, 50, 100, right? C, L, and so on. L1, 1, CX, 2, 2. So this is very primitive number system, but this is Roman numbers. Roman numbers, Roman people lived just before the European dominated. So that means the time of uh, Buddha, time of Jesus. So the time of Jesus or Buddha, they use this kind of numbers, right? This kind of numbers. So Jesus was born in ancient Rome, Roman Empire. Of course, it is Middle East, but it was under Roman Empire. So they use this. So this number system came even after that. So these numbers, like Roman, Greek, they were not positional numbers, non-positional numbers, non-positional. But these are positional numbers. Hindu Arabic numbers are positional. So this number system is very smart compared to this Greek, Roman number systems. So that is why a lot of things we get from Europeans, the science, a lot of math concepts, right? But number systems is from Hindu Arabic, India, Middle East, and this number system is accepted by Europeans. Whereas now we accept the other mathematical and scientific concepts coming from Europe. So what is cool about Hindu Arabic number system is the clever use of zero, and there's something called position. So the number depends on the position. Now here one is one everywhere. This is also one, this is two. And even here it is one because 5 minus 1. And this is 5 plus 1. This is 1 minus 10, which is 9. And this is 12. So whether it's here or here or here or here or here, 1 is 1. That is called non-positional numbers. That is not a very smart way to do. That is why you need more and more symbols, or the numbers become more and more lengthy. And when it comes to fractions and decimals, it become even more complicated. But this is a smart way. The smart thing is all about position, positional value. For example, when we say, now this is 5, this is 5, but this is not 8. This is 5, whereas this is 80. And this is not 5, this is 500. This is not 2, this is 2000. You can see that depending on the position, the same symbol has different meaning. But here this is 1, here also 1, here also 1, here also 1. But here, depending on the position, it has different meaning. So this is 5, this is 500, this is 80, this is 2000. So that is how positional number system work. Right? When it comes to positional number systems, we need a concept called base. We need a concept called base. For some reasons, these Hindu Arabic people, not only these people, even Roman people, so we settle pretty much to the base 10 for various reasons. 10 is our base. So that is why this is 500. This is why it is 80, because base is 10. This is 8 into 10 to the power 1. This is 5 into 10 to the power 3. This is 2 into 10 to the power 3. So therefore, whenever we talk about a number in modern number systems, there's a concept called number base. And as humans, our preferred number base is base 10. Right? Our preferred numbers base is what? Base 10. In base 10 numbers, we have 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when it comes to 10, you can write down that using these digits, or any number you can write using these digits. This is our 10, 11. So this is 159. You don't need more and more. That is why Roman numbers needed, right? X, V, C, L, and so on, because otherwise it's getting lengthy. Here also getting lengthy, but it's manageable length. Okay, so that is called base. So what is our preferred number base as humans? For historical reasons. Some people say it's because we have 10 fingers and so many reasons are given. But anyway, it is base 10 or denary. And remember, you need to remember two things. Our modern number system is a positional number system, not like Roman no Greek numbers. That is number one. Number two is our preferred base is base 10 in day-to-day life. That is how Hindu Arabic number system evolved. But it doesn't mean that base 10 is the only base we can use, right? So the concept of numbers can be extended to any base. Base 2, base 3, base 4, base 5, base 6, base 7, base 11, 12, 13, 14, 6, 15, 16, or base 100, base 5,000, or whatever. Just we have decided to base 10 as our preferred base. Whenever we write a number, implicitly we consider that it is base 10. Okay? But we can extend that concept to any base. For example, computers represent data using base 2. Of course, computer represent data using numbers. But computer use base 2 rather than base 10. Not only base 2, if you want, you can represent any number using base 3, base 4, base 5, base 6. For example, we heavily use octal and hexadecimal in our day-to-day, not day-to-day life, in some technical usages. For example, colors. So we represent colors using hexadecimal, right? F2, D5, A0, red, green, blue. Modern IP addresses are represented using hexadecimal numbers, version 6 IP addresses. So therefore, we heavily use in technical things, we use even hexadecimal, base 16. But anyway, for computer, the preferred base that the computer engineers, electronic engineers selected is base 2. Like base 2. So as I told you, especially in digital electronics, sometimes we use base 8, base 16 as well. So then someone might ask, why are we interested in base 8 and base 16 in computing and digital electronic? So the main reason is 8 and 16 has a connection to 2. For example, this is 2 to the power 3. This is 2 to the power 4. Therefore, 2 to the powers are more related to base 2, or binary. That is why sometimes we prefer to keep some values in base 8 and 16 as well. But inside the computer, everything is base 2. Everything is base 2. Okay? Right. So you need to understand this as a IT student, not purely like a math student, right? Because we are going to use it practically in digital electronic computing. Right. So now we must understand that there are two type of number systems, non-positional like Greek and Roman numbers, and positional. The modern numbers are positional, Hindu Arabic numbers. And also we have a concept called number base. As for general usage, we use base 10, but computer use base 2. And we can extend that concept to any base. And we are really interested in octal and hexadecimal also because those are more closely related to base 2. But our main focus is obviously base 2 because base 10 we are already familiar. Okay. Right. So this is what you're supposed to understand in this particular topic. So you must be able to convert base 10 numbers, or sometimes we call it decimal or denary, into any other base, especially octal, hexadecimal, and binary. or in any other base, maybe base 5, base 7, base 13. Okay. But we are more interested in these three. Okay. And not only that, you must be able to convert between these bases also directly, right? Binary to hexadecimal, hexadecimal to binary, and so on. So that is your competency number one. So at the end of today's session, you must be able to do this. Second thing is you must be able to do arithmetic operations, basic arithmetic operations using any of these bases, binary, octal, hexadecimal, obviously decimal, or any other base, say base 7. Can you add, subtract, multiply, divide? Okay. So in other words, so you must be able to think about numbers without restricted to base 10. Without restricted to base 10. So you just, because this, then only you get the correct understanding about numbers. Otherwise, you are restricted to one base. It is like if you know only one language, that is a big problem. That is why we have a lot of issues, conflicts. Some people know only one language. So then they think that that is the best language. So they think that their language is the best language, their race is the best race, supreme race, their religion is the truth. But if you learn more other things, alternatives, challenging facts, so then only you get a good understanding about the what is your thing and what are the pros and cons and so on. So therefore, at the end of today's session, so you should be able to get very good understanding about what is numbers, what is arithmetic, what is mean by addition, what is mean by subtraction, because you are not going to limit to number base 10. Okay. It's like when you learn two, three languages, only you get a very good understanding about what is a language is. Right? What are the pros and cons of languages? Why some languages are better than others for some certain tasks? Okay, so you must have the similar sense at the end of, if you do it properly, right? Without just concentrating on the exams. Okay, if you are thinking of a career in ICT, IT field, maybe AI, machine learning, and so on. Right. So we'll start with base 10 numbers because base 10 numbers are the numbers that we are very comfortable. Right. Base 10 positional numbers. So there we use 10 digits, 0 to 9. And because it is positional numbers, so the rightmost number is ones, 10 to the power zeros. So then we have tens, hundreds, thousands, 10,000s. In other words, 10 to the power zeros, 10 to the power ones, 10 to the power twos, and so on. Okay. For example, if someone says the number is, say, 8,725. So what does it mean? Right? We use the word 8,000 to 725. This is 5 into 10 to the power zeros or ones. This is 2 into 10 to the power 1 or tens. This is 7 into 10 to the power 2 or hundreds. This is 8 into thousands or 10 to the power threes. So therefore, this is 8,725. Yes, 8,725. That is because we use base 10. Okay, that is because we use base 10. Now let's apply the same thing to base 2. Now, if it is a binary number, now you have only two digits to play around, 0 and 1. So earlier we used 10 to the powers. Remember, still we use positional number system, but base 2 positional numbers. So now we have the rightmost one is 2 to the power 0, still it is 1. But now it is 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on. So in other words, now we have 2s, 4s, 8s, 60s, 16s, 32, 40s, 64s, and so on. So now if you write a number and say that you are writing it in binary, like this. Now you should know what is this number is. You must know it, not like a robot, right? Knowing the theory behind this, concept behind this, idea behind this. That is called understanding. So what is this number? Now this is the rightmost is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6. In other words, these are ones, twos, fours, 8, 16, 32, 64. So I have one, no ones, but one twos. So therefore it is 2. No fours, but 8. And there's a 16. And no 32, but there's a 64. So therefore, what is this number? You just add it. 8 plus 2 is 10, 6 plus 4 is 10, 10 plus 2, 10 is 20, 90. Now I can say 90 because we converted it to base 10. But this is not right 100 plus 1 million something. This is 10111010. But this is now 90. That is now 90. Is it clear? So that is how you convert binary number into decimal with solid reason, logic. Now it is a base 3 number. It is 3 to the power 0, 3 to the power 1, 3 to the power 2s. And base 3 number, you can have 0, 1, and 2 as digits. So likewise, you need to look at it in a general manner. Right. Convert this into base 10 quickly. Take a piece of paper and do it quickly. 1, 0, 1, 0, 0, 1, 0. Right. So this is 2 to the power 0, 2 to the power 1, or in other words, 1s, 2s, 4s, 8, 16, 32, and 64. And this number is 2 plus 16 plus 64. 12, 82 in base 10. So this number is 82 in base 10. Okay. Right. So you must do it knowing what you are doing. Okay. Knowing what you are doing. Right. So now let's see how to convert it in the backward way. So that is when you are given the binary number, convert to base 10. But sometimes we need to do, we have the base 10 number, say 2583. Can you convert it to a binary number? So there's a technique. There's a technique. What is that technique? You have done this in your O level. You keep divide this number by 2 and always write the remainder. Write the value remainder and then again divide by 2, write the remainder. If remainder is 0, you need to write 0. When you divide by number divide by 2, always the remainder is 0 or 1. When you divide the number by 10, remainder is between 0 to 9. So therefore it's always 0 or 1. And when you get 0 here, you stop. Then you write your remainders from bottom to top. And that is your binary number. So mathematicians identify this technique. Right. So let's do an example. Say 18. So we want to convert into binary. How do you do that? You keep divide by 2. 9, 0. 4, 1 remains. 2, nothing remains. 1, nothing remains. 1 remains. So now you can stop. Write your remainders from bottom to top. 1, 0, 0, 1, 0 in base 2. Don't say this is 10,010. 10010 because this is two. This is not one. This is not ones, tens, hundred, thousands. No, this is ones, twos, fours, eight, 16. So that is why it is wrong to say that this is 10,000. This is 10010 base 2. Okay. So we must use the words in a very precise manner, not in a very vague manner. Right. We must tell something knowing what we tell, like meaning. Right. So the answer is 10010 in base 2. I'm not going to do a lot of questions, just one exercise only because the same way, right? Whether you convert 100 numbers or whatever. Right. So this is only exercise. Just do this. Convert 156 into base 2. You know the technique. Keep divide by 2 until you get remain the value 0. Right. So this is 78, nothing remains. 39, nothing remains. 19, 1 remains. 9, 1 remains. 4, 1 remains. 2, nothing remains. 1, nothing remains. 0, 1 remains. So then you write it remainders in the reverse order. So the final answer is 100 111 in base 2. Simple as that. Okay, 100 111 So that is how you convert base 10 whole number, right? Still we work with integers actually, positive numbers, not decimals, fractions that we will discuss later. Okay. But you must be serious here because if you are not very serious and understand these concepts when it comes to fractions, negative numbers, you really mess it. You really mess it. Then you start memorizing without understanding. That is the vicious cycle. Okay. Right. So the second exercise you can do by yourself. Okay. Because it's the same way. Right. So now you know how to convert base 2 number to base 10, base 10 number to base 2. Now we will look at octal. So then someone will ask, why do you jump from base 2 to base 8 rather than we talk about base 3, base 4? I told you we are more interested in 2 to the powers. Okay. So then someone will ask, why don't you talk about base 4? Right? Because 4 is also 2 to the power, right? If you are a critical thinker, you must ask those things. Again, we are not much interested in base 4 simply because 4 is very close to 2. Okay. So therefore, we take something like 8 because our 1 byte is also 8 bits. Remember, we discussed in the I think when we discussed about the compute, introduction to computer, so we use byte, 8 bits, 8 bits. 8 bits we consider as 1 byte because 1 bit is too small, right? Then we can say 2 bytes, 4 bytes. But actually, before bytes, they use something called nibbles every 4 bit. 4 bit is called nibble. But now we don't use the word nibble because 4 bit is too small. So now our smallest unit is like 1 centimeter is 10 millimeters, uh, 8 bits. So that is why we are into the octal now, not base 4, because even we don't use the nibbles anymore as well. But of course, if you want to can think of base 4 numbers, not only base 4 numbers, base 3 numbers, base 5 numbers. Of course, you should be able to think, but we just consider some important bases for computing. Right. In octal numbers, remember in denary or base 10 numbers, we have 10 digits, 0 to 9. Binary, 2 digits, 0 and 1. So then octal, 8 digits, 0 to 7. 0 to 7. So we must be able to represent any number using 0 to 7 digits. And now it is 8 to the power. Okay. Your rightmost is 8 to the power 0 or 1, 8 to the power 1 or 8, 8 to the power 2 or 64, 8 to the power 3 or 512s, and so on. So on. So therefore, now you should be able to convert an octal number into base 10. So let's take an example. See, this is not 154. This is 154 in base 8. Right? 154 in base 8. So how do you convert this to base 10? So this is 8 to the power 0, 8 to the power 1, 8 to the power 2. In other words, these are 1s, 8s, and 64s. So we have 4 1s, 4 1s. We have 5 8s, that is 40. 8 into 5 is 40. And we have 164s, 108, because now this is 10, base 10. So 154 in base 8 is 108 in base 10. Here I can say 108 because this base 10. Okay. So now we have 8 to the powers. 8 to the power 0, 8 to the power 1, 8 to the power 2, and so on. Right, so this is the only exercise for you. Convert this base 8 number into base 10 or denary or decimal. So if you have any questions, you need to ask. Because if there are gaps, so then the vicious cycle starts. So then you start studying things you don't understand. So your task is make sure that you don't get any that kind of that gaps. If you get that gaps, you fill it by talking to ChatGPT, think about it, talk to others. Right. So this is never ever say 1267 because this weight base 8. If someone say 1267 in base 8, we know that that guy has no sense about number bases. That guy is just a programmed robot. Okay. So 1267 in base 8. 8 to the power zeros, 8 to the power ones, 8 to the power twos, 8 to the power threes, ones, 8, 64s. What is 64 into 8? 5 12s. So therefore, what is this number? 7 ones. That is 7. 6 eights. 8 into 6, 48. 2 64s. That is 128. 1 5 12s. 10 18 25 2 6 8 9 695. Now I can say 695 because now we are in the base 10. 695. Okay. Right. So that is how you convert octal to decimal. Octal to decimal. Just consider these are base or the 8 power of 8s and position. So therefore, this is 6 eights. This is not 2 eights. This is 2 64s. Okay. Because it's base 8. Right. Now we move on to the other reverse conversion. When you are given base 10, you want to get it into base 8. Right? You want to get it into base 8. So that is super easy. Now you know the concept. How to convert base 10 to a binary? Keep divide by 2. So then how to convert base 10 into octal? You keep divide by 8. Now your remainder can be up to 7. Again, when you get 0, you stop and write the remainders in the reverse order. Okay. Right. So let's take 106. Divide by 8. Of course, if you can't find it difficult, just divide in normal way and take the results. 1, 8, 3, 24, 2 remains. 13, 2 remains. Again, divide by 8. 1, 5 remains. 0, 1 remains. 1, 5, 2 in base 8. 1, 5, 2 in base 8. Okay. Fine. So this is the only exercise for you. Convert this base 10 number into base 8. 1560. Actually, you are not learning anything new today, but maybe we just better organize it in the context of ICT. You had done all these things in your level, grade 8, grade 9 or something. The other thing is you must be really comfortable with binary numbers. When we work with operating systems like memory management, uh, IP addresses, we work in base 2. I divide in IP addresses for the sub networks and so on. For those two topics, we need binary numbers. For any other topic, you don't need any of the maths, programming, databases. No, you don't need any maths knowledge. Fine. So this is 1, 8, 7 remains. So 76, 9, 72, 4, 40 means 5, 195, nothing remains. Nothing remains. So then I can again divide by 8. 216, 195. Let's divide like this. 35, 432, 3 remains. So that is 24, 3 remains. 3, nothing remains. 0, 3 remains. Is it 3030? 3030. Yes, 3030. Okay. So, right, that's it. So this exercise you can do by yourself because the answer is also given. Right, now we move on to our final base, hexadecimal. That is final base that we formally discussed, but in the exams you can get conversion question in any base, arithmetic question in any base. Okay, but using these three, you should get the understand so that you can apply it in any base. Okay, that is why we are doing it for 3 bases. Uh, right now, this one is slightly different. Actually, base is base. The concept is the same, but the only difference is so far we had only less 10 or less than 10 digits, but this is hexadecimal, base 16. So therefore we need 16 digits, 16 different symbols. So we managed to use the base 10 digits for binary and octal because when we have 10 digits, of course, we can just take the first set of digits. But now we need 16 digits. We have only 10 digits in standard base 10 arithmetic or symbols. So rather than coming up with new symbols for 11, 12, and so on, mathematicians have decided, okay, let's stop this because then if someone talk about number base, say 30, you need 30 symbols, right? It's a headache. So let's use alphabetical characters from 10 onwards, 10 onwards. So therefore, of course, if you want, you can use any other symbol, but everyone must agree, right? So now people have agreed, okay, let's say 10 is A, 11 is B, and so on, then 15 is your F. So then if it is base 17, you can even say G is your base digit 16 and so on. So that make our life easy. Okay. So therefore now we borrow few digits for few alphabetical characters also for 10, 11, 12, 13, 14, and 15. Because we need 16 digits. Remember 16 digit means 0 to 15. Base 10 means 0 to 9. See the pattern. Base 2 means 0 to 1. Base 2 means 2 digit, yes, but it's the digit 2 is not there. In base 10, digit 10 is not there. In base 16, digit 16 is not there. Digit 15 is there. F. So now you know the pattern. Now what you have is because it's the positional numbers. If we talk about positional numbers, now it is 16 to the power 0 or 1, 16 to the power 1 or 16, 16 to the power 2 or 256 and so on. Okay. So let's convert hexadecimal to decimal. Remember now you can have A, B, C, D, E, F as well in any place. And so this number is 1B4 in base 16. So we want to convert it to base 10. Remember this is 16 to the power 0. So once 16 to the power 1, so 16. 16 to the power 2 or 256. So we have four ones. Four ones. That is 4. We have B16s. Remember A is 10, B is 11. That is 11 16s. 16 into 16. 16 into 11. That is 16 and 16. 176. And 1, 256. That is 256. 6 plus 4, 10. 10 plus 6, 16. 6 plus 7 is 13. 2 plus 1 is 4. 436. Now I can say 436 because it's base 10. 436. Okay. So that is how you convert hexadecimal to decimal. Right? Hexadecimal to decimal. Is it clear? Right. So this is the only exercise for you. Convert this 1BF. This is ABF. Convert this into base 10. Take 1 minute. Right. So this is 16 to the power zeros or ones, 16 to the power ones or 16s, 16 to the power 2 or 256. So we have F means 16 number of ones. B number of 16s. B is 11 number of 16s. 176. And we have A number of 256. A is 10. 10 number of 256 is 2560. 12, 15, 7, 2752. 2752. Simple as that. Okay. Right. So that is how you convert base 16 into base 10. Right. Now you know what is our next thing, right? Next thing is obviously converting hex decimal to hexadecimal. And you know how to do it now also because now you should see the pattern. So if you are intelligent now, you should see the pattern. So that is why we are doing it for three bases, 2, 8, 16. Because you need at least three to see the pattern. See the pattern. Right. Now how do you convert decimal to hexadecimal? You keep divided by 16. And now the remainder can be up to 15. Up to 15. So if your remainder is 11, 10, you need to write it as A. If the remainder is 11, B. If the remainder is 15, F. So therefore, now you are going to get 0 to 9 and then up to F as your numbers. And again, you write it in the reverse order. Okay, right. So let's do one example and one exercise. 984. 984. So how do you do that? Keep divide by 16. Right. Let's do it here. Say 5, 33, 80. No, not 5, 6. 6 into 6, 36, 3. 6 plus 3, 96, yes. Then 24, 1, 8 remains. So 61, 8 remains. Divide by 60. Right? 61 divided by 60. 30. 3 and 30. And obviously when this is divided by 16, 0 and 3 remains. Now what is 13? Remember A, B, C, D. 10, 11, 10, 11, 12, 13. So D is 13 is D. Now you write like this 3D8. Final answer is 3D8. Okay, 3D8. Right, so this is your only exercise. Right, convert this. So then we are done with the conversion part. Now we are doing only 2 hours. So therefore, basically we want to concentrate on your syllabus and finish it very quickly, okay? So this is not time passing. Be very productive in this very short period. Right. So let's divide 10,767 by 16. Obviously, no 16 for 10, but 178. Yes. Just think of 15. 15, 30, 45, 60, 90. Uh, then 105. Yes. Possibly 6. No, 105 is not going to work because then 36. Yeah, 96, right? Yes. 6 into 6 is 36. 3. 6 plus 3 is 96. 7 minus 6 is 1. 10 minus 9 is 1. Then 117. 117 means again 6. So no, 7, right? 7. 7 into 6 is 35, 42. 4. 7 plus 4. 112. 4 remains. Sorry, 5 remains. That is 67. 5 remains. 5 remains. Again divide by 16. 4. 64. 3 remains. 0, 4 remains. 435 in hexadecimal, right? Is it 435? Or did I make a mistake? Oh, I have made a mistake, right? Yeah, I have made a mistake. Let's do it again. Let's do it again, okay? I have made a mistake. In this step itself, 6. Oh, I have forget one more place. Right, 16 divided 1,076,7 divided by 6. 6 into 6 is 36, 96, correct? 7 minus 6 is 1. 10 minus 9 is 1. Then this is 6, right? Yes, that is a mistake. So this 6 I want to take. Right, I made a mistake there. So this is 7 minus 6 is 1. 10 minus 9 is 1. Then we need to take this 6, 116. Right, 116, that is a mistake. Then how many 16 for 116? 7. That's 7. 7 into 6. 6 into 6 is 36. 36 plus 6 is 42. 4. 7 plus 4, 112. 4 remains, right? Yes. 6, 7. So 4 remains. Then you need to take 7. How many 16 for 47? 3. Sorry, 2. 2. 32. 15 remains. So therefore 673, 673 and 15 remain. 15 means F. 15 means F. Right? 15 means F. 15 means F. So then 673 you need to divide by, sorry, 672 you need to divide by 16. So then you get 42 and 0 remains. Then divide 42 by 16, you get 2 and 10 remain because 32 and another 10. Then of course 2, nothing and 2 remains. So therefore 10 is A, 15 is F, 2A 0F, right? 2A 0F. Yes, the answer is 2A 0F. Okay. Right, so this exercise you can do by yourself. Okay, so make sure you don't make mistake like me, okay? Right, so that's it. That is how you convert between uh, base 10 and base 8, base 10 and base 16. Right? Base 10 and base 8, base 10 and base 16. Now you know these things. What are these things? how to convert between base 10 to base 2, base 2 to base 10. Then how to convert base 10 to base 8, a base 8 to base 2. How to convert base 10 to base 16, base 16 to base 10. Or in other words, how to convert from base 10 to any base. Any base. Okay. Right. Now you want to know, can I convert base 2 to base 8 directly without going through base 10? And also base 2 to base 16, base 16 to base 2 directly without going. Of course, you can go through base 10, but it take more time. There are two reasons why you learn this. Base 2 to base 8, base 8 to base 2, and base 2 to base 16, 16 to 2. Two reasons. One, computer does this conversion directly. Because for computer, it is easier to convert directly rather than going through 10. That is the reason number one. And reason number two is in the exams, if you are given, say, base 2 number and asked to convert to base 16, if you go through this part, it take more time. So that means you lose some time because your A-level ICT exam is a competition. So therefore, if you know the direct conversion, which is easy, uh, you can do it with less time. Okay, so those are the two reasons. Actually, the main reason is the first reason. Okay, right. How do you convert 2 to 8, 8 to 2 directly? Very easy. Say you have base 2 number, and you are supposed to convert it to octal. So your task is very easy. Break it into chunk of 3 digits, but you need to break it from the right end. 1, 2, 3. 1, 2, 3. If you don't have 3 digits, don't worry. Just take the remaining digits. Now convert this 3 digit number into base 10, and don't worry, it is going to be something between 0 to 8 because the maximum is 7. So it will be 0 to 7. For the minimum is 0. So therefore, just convert to base 10, but it will be a valid octal digit. So this is 1, 2. 1 plus 2 plus 4, that is 7. 1 plus 2 is 3, and this is your octal now. So you can see this is super fast. Right? Super fast. 3, 7, don't say 372 because this is octal. 372 in octal. So if you get a question, if you convert to base 10 and come to this, you lose your this precious 1 or 2 minutes in the exam. But this is you just look at it and write. Right. So just do one more exercise. Convert this into octal without wasting your time. Okay. 1, 2, 3. 1, 2, 3. 1, 2, 3. Now you can just write it. 1, 2 plus 1 is 3. 2 plus 4 is 6. 1 plus 2 plus. Anyway, this you can remember always as 7. 7, 6, 3, 1 in base 8. And 7, 6, 3, 1. Right. So what about the other way? Of course, you need to do the reverse thing, right? Use your common sense. So if you are given this the eight octal number and ask you to convert to binary, can you do it? If you have the common sense, logical thinking, you know what to do. Okay, right? What to do? Take your number, write it as 3 digit binary. Always 3 digit. If you don't have 3 digit, prefix zeros. and that is your binary number. So you should be able to do from here to here as well as here to here. Pure logic. And so let's do it as a formal example. Right. Say this is my number 6252 in base 8. Now my task is convert to binary. Of course, I can convert to base 10 and count, but that take a lot of time. So write it in 3-digit binary, always 3-digit. 2 is 0, 1, 0, 1, 2. 5 is 4 and 1, 1, 2, 4, 4 plus 1. 2 is 0, 1, 0. This is 2, 1, 2, 4. 6 is 4 and 2, 1, 1, 0, 1, 2, 4. And this is your number. And here, if you get zeros, you can ignore. But these zeros, you can't ignore. 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. Okay. Right. Do this as exercise because these are super easy. So I don't know why some students say some systems are difficult. I don't know. Maybe they don't have the logical thinking. And do it fast because otherwise when you go to the exams, so you find that you are slow, right, compared to others. That is why when you have your friends also, make sure you have more friends who are faster than you, better than you, so they can even challenge you. And two is 0, 1, 0. 6 is 1, 1, 0. 4 and 2 is 6. 5 is 4 and 1. 4 is 1, 0, 0. 1, 2, 4. This is 4 and 1, 5. So the final answer is 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0. Okay. Right. So that is octal to binary and binary to octal. So remember, we think in terms of chunk of 3 digits. Chunk of 3 digits. Now you can guess what happens if you want to convert of binary to hexadecimal and hexadecimal to binary. If you have a bit of logical thinking, now you can at least guess what to do. Remember, when we work with octal, it's chunk of 3 because 2 to the power 3 is 8. But if you work with binary and hexadecimal, it is chunk of 4 because 2 to the power 4 is 16. Same thing, now you think in terms of chunk of 4, block of 4. That's it. The entire logic is the same. Okay? Right. Binary to hexadecimal. Now you think in terms of block of 4 digits. Let's straight away do example because now you can guess. So you want to convert this binary to hexadecimal. If you do it through base 10, you waste your time. And computer doesn't do it like that also. So therefore you are not going according to the process. Now break it into chunk of 4. One from right hand side. 1, 2, 3, 4. 1, 2, 3, 4. Right. Now convert this into base 10. But write it as a hexadecimal digit because the maximum you get is now 15. 1111 is 15. Of course, 15 is F. So therefore, convert it to base 10. But write it using hexadecimal digits. Okay. And so this is what? 1, 2, 4. 4 plus 2 is 6. This is 2, 4, 8. That is 10 and 8 plus 4 is 12. 12 plus 2, 14. What is 14? A, B, C, D. 10, 11, 12, 13, 14. E. Right, so this is 14. 14 means E. So therefore my number is E6 in hexadecimal. Convert to base 10, but write using hexadecimal digits. Take chunk of 4 from right hand side. Okay, E6. That is super fast. Right, so this is your only exercise. You don't need to worry about how long it is because you take chunk of 4, right? But if you convert this into base 10 and come, okay, that you will fed up with your exam also because it's a huge number. But this is super easy, right? Do it. Right. You need to break it into chunk of 4 digits from right hand end. Okay, right hand end. 4, 4, 4. Now it's piece of cake. This is 3. This is 7. This is 1, 2, 4, 8. That is 12 plus 1, 13. 13 is A, B, C, D, E. 10, 11, 12, 13, D. This is 7. 7, D, 7, 3. This binary number is 7D73. 7D73. Right. So now you know what is our next task. This is converting binary to hexadecimal. Obviously, the next thing is uh, hexadecimal to binary. Can you convert this hexadecimal to binary? Can you convert this hexadecimal to binary? Now you know the reverse process, right? Common sense, logical thinking. Right. You convert each into 4 digits binary, and then that is your binary. Okay. Hexadecimal to binary. Right. Let's straight away do example because you know now the approach, right? Logic. Right. So this is my binary number, hexadecimal number. B5A. I want to convert it to binary. Of course, if you want, you can convert it to base 10 and binary, but it will take more time, frustration. But this is easy. Right? Take your number as base 10 number. Convert it to 4-digit binary. If it is less than 4 digits, prefix zeros. And then your binary number is ready. Right? A is 10. So convert 10 into binary. Uh, let's do it in the other way. We want to convert to binary, right? A is 10, okay? 5, nothing remains. 2, 1 remains. 1, nothing remains. 0, 1 remains. 1, 0, 1, 0. You can double check, okay? 1, 2, 4, 8. 8 plus 2 is 10, correct. Then 5 is 4 and 1. 1, 2, 4. Then this is 0. 1, 2, 4. 4 plus 1 is 5. B is A plus 1. Right? So rather than convert 11, what is the next number after this? 1, 0, 1, 0. Next number is 1, 0, 1, 1. That is how you preserve your time. Be smart. So smart people will never complain saying time is not enough. And this is your answer. 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0. Okay. 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0. Correct. Right. So this is for you. And be smart, be quick, be efficient. At the same time, be accurate. Don't make silly mistakes. Right. So convert one by one. 9. Convert to binary, but 4 digits. Right. Let's convert like this. 9. 4, 1 remains. 2, nothing remains. 1, nothing remains. 0, 1 remain. 1, 0, 0, 1. Yes, 8 plus 1 is 9. Then A is 10. 10 is 1 bigger than 9. 1 bigger than 9 means 1, 0, 1, 0. And of course, 8 plus 2. There are different ways you can think quickly. Okay, think quickly. So then F is obviously the biggest number, right? F is 15, that is obviously 1, 1, 1, 1. 1, 2, 4, 8, 16 minus 1. F is 15. So 8. 8 is obviously 1, 2, 4, 8. Right? 8. So this is your number. 1 triple 0, 4 ones, 1 0 1 0 1 double 0 1. Be smart, right? So that will preserve, right, split of seconds. Right? 1 triple 0, 1 1 1 1, 1 0 1 0, 1 double 0 1. Correct. Right? That's it about conversion between our famous number bases. Right? Famous number bases. That is base 2, base 8, base 16. So our next subtopic is representing fractions in these bases or any other base. But before moving to that, we want to discuss, I want to double check whether have you got that understanding? Have you got that confidence? Okay, so I will give you just one, two exercises uh, just to check whether you have got that confidence, understanding. Okay, I convert this base 10 number into base 12. Right, quickly do it. So if you can do it, you have understood it. Simple as that. If you can't do it, still you are not very comfortable with, you don't have a deep understanding. Maybe you are just understanding things, that small things we do without trying to get the big context. Or you are not very good at getting the patterns. So use your common sense, logical thinking, critical thinking, intelligence, that is seeing the patterns, convert this into base 12. Make your decisions. Life is like that. Life is a journey into the unknown territories. But use your experience. That is why some people are successful in their life, some people are not that successful because they can't survive in unknown territories. Yes, base 12. Base 12. You need to convert it to base 10 number into base 12. Sorry, I forget to mention it, base 10. Even in A-level exam, they have given this kind of questions because in the A-level exam, they check whether you have that deep understanding and the examiner want to challenge you, not teach you something and ask the same questions, right? That is not ICT. Maybe that's some other subjects. Now, when you convert to base 2, you keep divide by 2. When you convert to base 8, you keep divide by 8. When you convert to base 16, you keep divide by 16. So then you must know what your what should be the what should I do if I want to convert to base 12? That is called intelligence. See the patterns. So gradually you need to build that confidence, skills.
258.
It doesn't. It's okay if your answer is not correct, but give a try. Okay, 25A. Okay, let's see whether the answer is correct. Right, I got the answer as 25A. Right, so let's see. So if you are supposed to convert to base 12, what your task is divide by 12, right? Divide by 12. If you convert to when you convert to base 16, if you divide by 16, right? When you convert to binary, if you divide by 2, so if you are supposed to convert to base 12, you are supposed to divide by 12. Obviously, right? Right, so let's do it. 358. Let's divide by 12. 2, 4, 24. 5 minus 4 is 1. 3 minus 2 is 1. 11. Yes, you can have 11 remains. So then you need to take 8. 118, it must be 9, right? Because then you have 120. 9. 9 into 2 is 18. 1, right? So then 9 plus 1, 10. Then this is 0. This is 10. Right? So that is 29. Remainder is 10. So then again divide by 12. Obviously 2, 24. 5 remains. 5 remains. So then 0, 2 remains. So A you can't write because A is, sorry, 10 is, you can't write. 10 is A because you can use the same convention. 10 is A. So therefore it is 25A in base 12. Yes, your answer is correct. 25A in base 12. Okay, right. So that is the first exercise. Likewise, it can be base 3, base 5, base 7, base 21. Who cares? Right. And so this is your our next exercise. This is easy actually. Say this is my number. 3605 in base 7. Convert this into base 10. Okay, so I'll make it shorter. 365 in base 7 convert to base 10. Right, so this won't take much time. This is a base 7 number. Right. What is the answer? 194. Okay, let's see. Let's see. Let's see whether it's 194 in base 10. Now this is base 7. So if base 7, this is 7 to the power 0, 7 to the power 1, 7 to the power 2s. In other words, these are 1s, 7s, and this is 49s. Okay, 7 to the power 2 is 7 into 7. So we have 5 ones, that is 5. We have 6 sevens. So 6, 7 means 7 into 5 is 35, 42, right? And we have 3 49s. So 349 means 150 minus 3, 147, right? Then add it. 5 plus 2 is 7. 7 plus 7 is 14. 1. 4 plus 4 is 8. 8 plus 1, 9. Yes. 194. Answer is correct. Okay. Right. So that is how you convert. So therefore, now you must be really comfortable. You don't care whether it's base 2 or base 5 or base 7 or base 13 or base, right, 25. Numbers are numbers. Number base is just a concept. Okay. Right. So far, what we have discussed is how to represent numbers or the whole numbers or the integers in different bases. But remember, when it comes real numbers, we have fraction parts also, right? Like zero point 0.7, like 0.25, point, or maybe 1.35. So how do you convert it to base 2 or whatever the base? Okay, that is our next subtopic. Again, we are more interested in decimal and binary. Of course, you can extend it to octal and hexadecimal, but we are more interested in decimal and obviously you know decimal. We are more interested in binary, but we can extend it to any base, even hexadecimal or base 12 or base 7 or whatever. Okay. But our exercises will be more towards binary. Right. So this is let's again start with something we know. So this is base 10 decimal or fraction 0.752. First of all, you must notice that we don't say 0.752 because I have heard that some students call it 0.752. So that clearly show they have no idea about what they are talking because this is not 700. 700 is something like this. Now this is 705. This is not 700. If you say 700, 0.752, it's basically nonsense, right? Nonsense. Just use words without knowing what they talk about. Right. So therefore, this is 0.752. Remember, if it is something like this is 10 to the power 0 or 1s, 10 to the power 1 or tens, say 10 to the power 2 or 100. So therefore, here 625. But this is 10 to the power minus 1 or 1/10 or point ones. This is 10 to the power minus 2 or 1 over 100 or 0.01s. This is 10 to the power minus 3 or 1 over 1000 or 0.001. So this is zero point 0.1. So 0.1 into 7 is 7. 0.01 into 5 is 7.5. Yes, right? Likewise. So this best way to tell it, or not the best way, the correct way is 625.752 because this is zero point 0.1 into 7 is 0.7. Okay. And this is 0.05. This is 0.002. So therefore, it's correct to say 752. So you must know what you are talking about, right? And why do we speak like that? Right. So that is base 10. Now you can think, adjust your thinking to base 2, base 5, base 8, base 16. Okay. Now, if it in base 10, if it is 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3, if it is base 1, obviously this is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. Say you have something like this. So this is 2 to the power 1, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. And then this is 2 to the power minus 1 or half or 0.5. Remember, this is 1, 2, 4, 8, 16. And this is 0.5. This is 2 to the power minus 2 or 1 over 4 or 0.25. It's 2 to the power minus 3 or 1 over 8 or half of this. Now remember, multiply by 2 here, divide by 2. See the patterns. Twice, 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 half of 0.5, half of 0.25. That is 0.125. Next one will be half of 0.125. 0.625. Right. So let's convert this number into the binary. Sorry, base 10. Okay. So therefore, this is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. In other words, this is 1 over 2, 1 over 4, 1 over 8. In other words, this is 0.5. This is 0.25. This is half of 0.25, 0.125. And we don't have any 0.5s, 0. But we have 1.25. 0.25 into 1 is 0.25. And we have 1.125. Either you have 1 or nothing. Okay, so therefore we have 0.125. So the 573. So this number is in base 10, 0.375. Simple as that. Okay, 0.375. So what you have is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and so on in base 2. If it is base 8, to 8 to the power minus 1, 8 to the power minus 2, 8 to the power minus 3. If it is base 16, 16 to the power minus 1, 16 to the power minus 2. Now you know the pattern. Okay. Right. Convert this into base 10. This is only exercise. Convert this into base 10. It's a binary fraction. Still, we are not into representing data in computer. We are just doing maths topic, right? Maths topic. This is a number theory. Right. So this is 2 to the power minus 1, or you can straight away say 0.5. Then 2 to the power minus 2, or half of this 0.25. 2 to the power minus 3, or half of 0.25. 0.125. This is 2 to the power minus. So let's write it 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. This 2 to the power minus 4. So this is half, 1/4, 1/8, 1/16. 1/16th is half of this, half of 0.125. That is 0.0625. Now we have 1 of the 0.0625 and 1 0.125 and no 0.25, but we have 0.5. Add it. 5786, 0.6875 in base 10. And 0.6875. Yes, 0.6875. Okay. Right. So that is how you convert a binary fraction. I can't say binary decimal. Okay. So this is binary because not decimal, right? Or I can say binary fraction. Okay. Binary fraction into denary fraction or base 10 fraction. So you just consider it as 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4, and so on, or 0.5, 0.25, and so on. Okay. Right. How do you convert in the other way? So converting in the other way is a little bit more challenging. Remember how to convert decimal to binary? Like 35 into binary, you keep divide by 2. So then how do you convert something like 0.825 into binary? So this is decimal part. This is fraction part. Decimal part you keep divide by 2. Fraction part you keep multiply by 2. So that's a nice pattern. So then even if you forget it, again you have a way of access to that memory. Okay. So here you keep divide by 2. Here you keep multiply by 2. Here we keep writing the remainder. Here we keep looking at the whole number part. Okay, right. So let's do an example. Say this is my binary number, binary fraction, 0.75. I want to convert, sorry, this is my denary fraction. I want to convert it to binary fraction. So this is how you do it. You keep multiply by 2. You take only the decimal part. Of course, here you don't have the right. 0.75 into 2 is 1.5. Then take the decimal part. Decimal part only, and again multiply by 2. 1.0. When you get 0 here, you can stop. Then write your whole number part from top to bottom. In this case, 1, 1. So therefore, final answer is 0.11 in base 2. You can double check because this is zero point 0.5, this is 0.25, zero point 0.5 plus 0.25 is 0.75. Yes, answer is correct. Right? You can quick double check also. Right? Right. So let's do another example so that you better understand it. Right. So this is what we do. Right. So let's convert this one. So this one has both decimal part, fraction part, and whole part. The whole part will convert separate. Decimal part will convert separate. That is how we do it. Actually, you can't convert both part together. So let's do the easier part first. 40. Keep divide by 2. 7 nothing. 3 1. 1 1. Nothing 1. So the whole number part we have done 1110.1248. Yes, the 8 plus 4 is 12, 12 plus 2 is 14, correct. Now we take the other part, decimal part, 0.6875. You keep multiply by 2 until you get 0 for the decimal part. Or you feel like you have enough accuracy. If you don't get 0, you can stop saying that this is approximately this. Right, so let's multiply. 5 into 2 is 10, 1. 14 plus 1, 15, 1. 16 plus 1, 17, 1. 6 plus 1, 7. Sorry, uh, 10, 1, 14, 15, 1, 16, 17, 1. 12 plus 1, 13. Right. So now again take the decimal part. 0.375 multiply by 2. 10, 1, 15, 1. 6 plus 1, 7. Now, if there's no whole number part, just keep it 0. Again, take the decimal part. 2, that is 1.5. Still, we have decimal part. And now we are getting 1.0. When you get 0, you stop. And write your whole number part from top to bottom. Remember earlier, bottom to top. Here, top to bottom. 1, 0, 1, 0. And this is your number. So this number is this. Simple as that. Okay, simple as that. So it's a systematic approach. If you don't get zero, what happens? There can be such situation. You keep multiplying, but you don't get zero. Then after some time, you can say this is, say you don't get zero. So then you can say this is approximately this, because this part is not 100% accurately represented, but approximately. Of course, that is a common issue in computers. Common issue is computers. When you do Python programming, you will see that when we do a very simple division, right, you expect something like 0.75, but what you get is 0.749999 something. That is because there's a limitation in accuracy. Some numbers you can't 100% accurately represent. Okay. But maybe that inaccuracy is after 4 decimal places, 5 decimal places, usually we don't care. Okay. But if you need that high accuracy, you need to go for special data types. Right? So we will look at those things when we discuss representing data in computer. Right? Especially IEEE representation, what is 32-bit, IEEE 64-bit. Okay. Right. So now you know the theory. Now apply your general knowledge, common sense, and convert this octal fraction into decimal. Now this octal fraction, now use your common sense and write down what is this number in base 10. Right. I don't give any help. I assume you have that IQ. See the patterns. At least give a try. Just the rough answer is enough because I know that 8 to the powers are a little bit frustrating, but it's just two places, therefore it should not be that frustrating to calculate. Now remember, if it is octal, these are 8 to the power zeros, 8 to the power 1, 8 to the power 2, this side. But then this side is 8 to the power minus 1, 8 to the power minus 2. That means 1 over 8, 1 over 8 to the power 2, okay, or 1 over 64. So it's easier ways, just multiply this by this by this as a fraction. That is little bit easy because, okay, say 1 over 8 into 1 plus 1 over 64 into 4. That is 1 over 8 plus 1 over 124 is 16, right? That is 16, 2 plus 1. That is 3 divided by 16. So in the exams, if you get, usually the answer, there will be something like this. Or you divide this 3 divided by 16 and write maybe if it is MCQ, okay? Right. If it is 3 divided by 16, I will quickly use calculator. Uh, just to double check the answer. 3 divided by 16. That is 0.1875. Okay, 0.1875. Yes, 0.1874, 0.1875. It depends on the accuracy you go for. Okay, right. So that is how you convert. Right. So now you can convert the full number into octet. So this keep divide by 8. This keep multiply by 8. Keep divide by 8. This side keep multiplied by. Do the two parts separate. Right. Do it. Because now you want to convert this whole decimal and whole number part both into octet. So the idea is you get that confidence about number bases. So that confidence is super important to understand how the computer work. So then when you go for exams also, you go with lot of confidence, right? You're up to the challenge. Otherwise, when the exams are nearing, students get stress, right? So there are butterflies in their stomach because they are not up to the expectation. So you must be aggressive, right? So let's convert this 85. Keep divide by 8, 10, 80, then 5 remains because we want to convert it to octal, okay? 8, 1, 2 remains. Nothing, 1 remains. So that is 1, 2, 5. Now I want to convert this into octal. How to do that? Keep multiply by 8. Then you will get something between 0 to 7 in the whole number part, okay? 0.0625 multiply by 8. 8 into 5, 40. 4. 16 plus 4, 20. 2. 8 into 6, 48. 48 plus 2, 50. 5. That is 0.500. 0 point. Okay. So then take the fraction part again, 0.5 into 8. That is 4.0. Now we got the 0. You can stop. Whole number part is 0 and 4. That is your octal now. Okay. Same process, same logic. Okay. 125. Don't say 125. 125 point. This is 0.5. And 0.5 into 8 is 4. Then we are done because you got 0. You write from top to bottom. 125.04 in octal. Okay. Right. So our final thing is how to do arithmetic operations using any base. Right. So that I don't want to do it today because it will be too much for you. That we will discuss in the next class. It will take about another 1 hour because we want to do it in a proper way. And then in the next class, we move on to how to represent data in computer. Right. Second part of your syllabus. So first we will look at how to represent whole numbers, decimal numbers, characters, then very high level how to represent images, audio and video, but that is at very high level only. But we are dead serious about whole numbers, characters and little bit about decimals. Okay, right. So we stop at this point, right? Thank you.